Yeah, I think it's time and we could start the session. So good morning, everyone. My name is Ranjit Kumar Shanmugasundaram. Today, I would like to present my toolbox that what I've been developing for this NULIMAS project, which is for Seabed liquefaction. And so I'm Ranjit Kumar Shanmugasundaram. I'm actually working in Wikki GmbH, Germany as an engineer, and I'm also a PhD student at TU Braunschweig. And agenda for today is I would be giving you a brief introduction to liquefaction. After that, I'll be describing about the numerical model that I have developed or all the equations that I have developed for this NULIMAS. And after that, I'll be giving you a hands-on session on the pore pressure verification and then the shear stress. And also, I'll be giving, I'll be showing you cases where you could predict the onset of residual liquefaction. And further, if we have time, we could also go with the sensitivity analysis. So just to check how the parameters in the model are affecting the seabed liquefaction. And finally, I would be giving a brief introduction about the post-liquefaction model that I have developed, and I will be giving you some of the preliminary results that I have for the post-liquefaction that I have so far. And finally, I'll draw some conclusions, and I'll be giving a okay, and I'll be giving future works what I'm been doing in this project. And so, what is meant by liquefaction? Liquefaction is the process in which the seabed behaves like a highly viscous fluid. This phenomenon is mostly occurring in case of saturated soil, and in case of saturated soil, you have the soil skeleton completely filled with a liquid. In case of water, and whenever there is a water filled in case of the soil skeleton, you can see that there is a pressure acting on the water. And there is always a pressure between the soil grains in the water that is known as the pore water pressure, and this helps to have the soil particles attached to each other. And then finally, and also it also has a shear strength between the soil particles, which helps to withstand the loads. For example, gravity anchors, and then the marine structures, breakwater, something like this. So okay, whenever there is a loading on the soil, for example, in case of waves, you can see that there is a pressure applied on the top of the surface, and then it is trying to squeeze the soil seabed, and then the water is trying to run out of it. And in case of a drained soil, it is not a problem because the water can easily flow out of the soil. But in case of undrained soil, and you can see that the pressure between the soil grain is trying to increase, and then it cannot go out of the soil, so the pore pressure starts increasing, and at some point of time you can see that the pore pressure between the soil grains is greater than the effective stress in the soil, which makes the soil behave to start readily to move with respect to one another. So it is the case in which the seabed liquefaction starts. And what happens in that case is because it can readily move with respect to one another, and you can see that the soil can behave like a fluid. And this also makes this is also happening that in the soil also loses its capacity to withstand load. For example, in case of this breakwater, you can see it starts to go down, and also in case of buried pipelines, it starts to float, and so on. And so we don't want that to happen. So that brings us to this project, just NULIMAS, which means the numerical modeling of liquefaction around marine structures. And you can look out our website here. And what do we do in this project is we are developing an open source numerical software for predicting the onset of residual liquefaction. So we do it in OpenFOAM. And after that, what we will be doing is we will be comparing this numerical solutions, numerical results against the experimental test results that we have from our project partners, and also we have a large scale tests, and we will be finally comparing our model against the large scale tests. And this is the typical this is the case study that we have to will be doing in this project, where we have a seabed, and then it is attached to the we have a gravity anchor attached placed on the seabed, and it is connected to the wind turbines, and with the help of the floating offshore structures. And this exerts the there is a ropes connected to the floating of structures, and this exerts the force on the force on the gravity anchor, and there is the loading here, and then like this causes the seabed liquefaction, and there is failure of the marine structures. So this is the case study that we wanted to do in this project, and so that's what like we would be doing at the end of this project. And finally, I would like to show that like there is two different types of liquefaction, which is residual liquefaction and then the momentary liquefaction. And residual liquefaction is one in which it occurs in case of progressive waves. So when there is a progressive waves, there is a periodic variation in the seabed, and due to this alternating variations in the seabed, you can see that the shear stress changes, and that is causing that is causing the rearrangement of soil grains, and then it induces liquefaction. And so basically what I was telling you before, the pore pressure between the soil grains starts to increase, and then like whenever this pore pressure is greater than the effective stress of the soil, you can see that the seabed starting to liquefy. And finally, there is also another type of liquefaction, which is momentary liquefaction. This occurs mainly during the passage of wave troughs. So in unsaturated soil, there is a very high pressure gradient, and then this larger pressure gradients allows to generate the lift on the top surface of the soil, and then whenever the lift is greater than the submerged weight of the soil, the momentary liquefaction occurs. But this momentary liquefaction is a temporary phenomenon, and so it is not it's not really it's causing any damage. So this one will not be doing in our project. Like we'll not be doing this type of liquefaction in our project. And I would like to show that the time series of residual liquefaction. So in which liquefaction usually starts. It starts from here. So whenever the waves are switched on, you can see that the pore pressure, so this graph is against the pore pressure versus time, and during at the start of liquefaction, you can see that the pore pressure is starting to increase, and then at some point of time you can see that the pore pressure is it's reaching the initial effective stress of the soil, and then it's starting to behave like a fluid. It's the place where liquefaction starts, just like onset of liquefaction, and we would be developing in this. We'll be like showing in this training session. And what happens is in most of the present literatures, they are covering only till the onset of liquefaction. But in our project, like what we wanted to do is like we also wanted to predict what happens after the liquefaction. So we would be trying to do, we'll be trying to model this phenomenon as well. And what actually happens is whenever there is a pore pressure and it starts to increase, and then like we get a liquefaction, and the soil will behave like a fluid, and the liquefaction basically starts from the top of the soil, and then like it goes slowly to the bottom of the soil. And at some point of time, there is a pressure gradient occurring because the pore pressure starts to build up at the bottom of the soil. The rearrangement is its maximum at the bottom of the soil. Even then, the initial effective stress in the soil on the bottom on the top of the soil is low, so the liquefaction starts there. But at some point of time, it reaches down to the bottom, and then there is a larger pressure gradient occurring in the seabed. So this causes the water to move upwards, and then the soil grains to start settling down at the bottom. So that is known as the compaction. And based on our model, we would be trying to predict till the soil compaction. And this picture is the numerical representation of what I wanted to show what I was showing in the previous slide. So we have this seabed, and then we have a gravity anchor on the top, and this we have the forces connected to the floating offshore structures, and there would be this we will be representing this of the rope forces with boundary conditions, and mainly we would be distinguishing this model into three different categories and the three different regions. One is the waves on the seabed, and for the waves on the seabed, like we will be using just the pressure wave equations, so we can just include that in case of the boundary conditions. And then next one is the soil region. This is the most important part in our work. So this is the soil region. Like we consider the soil region as a poroelastic solid with an incompressible pore fluid. And finally, you have the liquefied region. So at the starting of the experiment, like you don't have the liquefaction. So this liquefied region is not there, and it actually starts like after some time. So after some time, when it starts, like it is all the constitutive relations of the soil changes, so it cannot be a poroelastic solid anymore, and it will be behaving like a fluid. So we need to have a different fluid, for example, the non-Newtonian fluids. So there are three different formulations in order to solve the solve the poroelastic solid. One is the fully dynamic form, and in which you have the acceleration of soil skeleton, and then the acceleration of pore water pressure relative to the soil skeleton, and then the partially dynamic form in which the acceleration of soil skeleton is present, but there is no acceleration of the pore water relative to the soil skeleton. And finally, you have the quasi-static approach, in which you don't have both the acceleration of soil skeleton and then the acceleration of pore water relative to the soil skeleton. And yeah, so what we had to do is, like, we wanted to build a very simple model with a less number of parameters, because like if we have a large number of parameters, and it would be very difficult to get it from the experiments, and then like it will be very difficult for us to validate at the end of the project. So we wanted to keep it simple, and then like we use for the quasi-steady bioequations where we don't have the any accelerations at all. In order to solve for that, we have the pore fluid continuity and then the linear momentum balance in the solid. So in the pore fluid continuity, you have the continuity equations where you have the Laplacian of the pressure, and here is the volumetric strain, rate of change of volumetric strain, and then finally the volume change due to the compressibility effects. And finally, the other one is the linear momentum balance, in which you have the divergence of stress equal to 0. And basically, in these two equations, we will be solving for the pressure and then the displacements. And then finally, we'll be using these displacements in the stress-strain relationship in order to get the stress. And from that, like, we would be able to calculate the different stresses, and then from that we will be able to predict the pressure buildup. And regarding the and then, yeah, so here you have the stress, and since I told you we are using a poroelastic solid, we have just the linear relationship between the displacement and then the stresses. So this is the first case study that I would like to show you. So where I was trying to validate the bioequations with against analytical solutions, and then for that I have a seabed, and then I do have the wave on the top, and then I have the different boundary conditions. I have the cyclic boundary conditions at the sides of the seabed, and then at the bottom I have the pressure gradient going to 0, and then the 0 displacement. And yeah, and this case is actually from the Schumann-Inks, and I will be doing the I'll be showing you the model. And those who would like to do with me, you can actually download the source code from GitHub. So it is available in so you can check out the link for the GitHub, which is github.com/NULIMAS. And yeah, in that, like, I have the workshop repository, and then like I'm going to directly get the source code from here. And then the OpenFOAM version that I have been using is Foam Extend 4.1, and I think it would be able to, you would be able to do the validation cases in the Foam Extend all the OpenFOAM versions, but like you just have to change some of the things. But it would be readily available with the Foam Extend 4.1, and so I already have it downloaded in my thing, but I would be just showing you how you can get it directly from the GitHub, and you can so I'm right now in the I'm right on in the master branch, and you can just do all wmake in order to compile all the boundary conditions and then the solvers. In the meanwhile, I'll be showing you where you can how the code has been implemented. And if you go into the source directory, you have the different solvers, and you have this BioQS form, which is the bio equations that I was showing you before. And so inside the bio equations, you have the pressure equations and then the displacement equation implemented. And if you just start from here, you can see that on the top you have the mesh and then the read material properties. And in the read material properties, you will be just reading all the material properties. For example, the elastic modulus, porosity, the what else? The Poisson ratio, the permeability, and then the bulk modulus. And yeah, here you have all the properties which is loaded from the input deck. And so here you have the pressure equations implemented, and then finally you have the displacement equations. and from there there is an inner loop which is be solving for the displacements, and then after that, like, you will be able to converge. You will be converging for the pressure and then the displacement. And yeah, so I think it should be done. No, not yet. And I have the example cases inside run folder. If you just go into the main folder and you have the run, and then like you have the shown Young's case, sorry, the validation analytical, and then you have the shown Young's case. Here what I have is, if you just look it into the material properties, and you have the elastic modulus, which I have it as 26 million pascals, and then the porosity is 0.3, sorry, the Poisson ratio is 0.33, and then the permeability it's very high of 0.001, and I have all the other parameters which is just given inside this. So in the OpenFOAM format, you know that there is here you have the units, which is kilogram, meters, and seconds for the first three, and you will be giving the values at the end. And then you can see that inside the shown Young's case, I have this all run script where it will be just running the block mesh and then the solver for you. And before that, I just like wanted to show you the place where you can change the time step size, and then how much runtime intervals you wanted to write it down, the results. And then you can see that inside the system control deck, you can look out for the time step that I use is 0.2, and the right interval is 1. I think it should be ready, and yeah, at least I think you can just do the mesh, and for the mesh you just have to run block mesh, and in the block mesh you can see that yeah, I think the BioFOAM has compiled, so I'll be running the BioFOAM solver. So this is the mesh that I've created. This is I think 50-meter deep, and then I have considered for one wavelength for the width, for the length, and then you can see that like I have a mesh of 100 by 50, and I think this is a bit slow. And so since I wanted to I wanted to verify the pressure and then the shear stress, I have those presented inside the function objects, and you can see that from the system function .h file that I have the function of object written for the profiles for the whole depth, and for 200 points for the field's pressure, displacement, and then the shear stress. I also have written an Octave script in that, like just to pick up all the data from the file, and then it also has the pick up the text file for the analytical results, and then like I will be comparing just to show the comparison against this numerical results. And you can see that I think it is done for 5 seconds, and I'm gonna kill this thing. And yeah, since it has done for 5 seconds, so my wave period in this case was 10, so you just have an half a cycle of wave, and yeah, so you can see here that like you have an alternating incremental and then the decremental the pressure, the positive and negative, and then finally you can see that with the time it just moves, and with the since you have the wave, and then like it is creating the pressure at the alternating incremental and expansion and the decremental of the pressure. And yeah, so you have the pressure and then the shear stress results stored in the post processing, because like I have written the function object for that, and finally I have the I have this Octave file where I can compile the results. I think I also have the results inside the presentation, and then so this is actually the analytical results of the pressure, and finally for the shear stress we have something like this. So we have a very good match against the very good agreement with the analytical results. And yeah, so but the problem with this case is like we are just solving for the instantaneous, and then so there is no rearrangement of soil grains, and then there is no, the pressure buildup is there. So in order to have the residual liquefaction, you need the rearrangement of soil grains, and then but the Biot equations does not include the rearrangement of soil grains. So there is a shear stress, and shear deformations will actually try to rearrange the soil grains, and then for that like you need to solve an additional equation such that like you have the pressure, it's the accumulation of pressure. So the small p inside the Biot equation, what we have is just the alternating pressure variations. And but in case of residual liquefaction, we wanted to have pressure buildup, and then that goes something like this with respect to time. And for that, like we need an additional equation, which is the just this Laplacian equation. This equation is just derived from the previous Biot equations, and with the source term, and this source term is dependent on the initial effective stress of the soil, number of cycles for liquefaction, and then the time period. And this number of cycles for liquefaction is basically dependent on the amplitude of the shear stress. And these alpha and beta are the coefficients, empirical coefficients dependent on the relative density of the soil. And I think in order to calculate the amplitude of the shear stress in the OpenFOAM, what we have is we cannot straight away have the amplitude of the shear stress. So because like we have the shear stress, and then we needed to calculate the root mean square of the shear stress, and then we have to take the amplitude from that. But in case of OpenFOAM or like in any other solvers, like you cannot get the amplitude of the shear stress initially, so that like you need to wait until one wave period in order to have an accurate amplitude of shear stress. So for that, what we have to do is we have to solve the we can approach actually in the two different cases. One in which we solve for the the equations till the one wave period, and then like we take the shear stress and then put it into this equations, and then we calculate for the accumulation of the pore pressure. And the other one is you can directly implement such that it is looking for the previous wave period, and then like it is trying to calculate calculate the shear stress from the previous wave periods. And so as I was mentioning before, like in order to have the onset of residual liquefaction, we have this criteria which says that whenever the pressure buildup is greater than the initial effective stress of the soil, the liquefaction starts to occur. And sorry? Yeah, yeah, we are right now dealing with the regular waves, but we haven't done with the irregular waves. I think like in case of irregular waves, we can do it in like a regular. We can adding different wave periods together, and then we can build up together. I mean, like what I was mentioning is you need to have the amplitude of shear stress that this it's to be constant. For example, when if it is regular and then it is static, so you can directly take it from the after one wave period or like after some time. So or actually the ideal thing would be to have the shear stress already, or the shear stress calculating from somewhere, and then like it is putting into the equation. And yeah, in case of irregular waves, like everything would be changing. For example, the boundary conditions and then the other stuffs as well. So that also like we have to take into consideration. But right now, like what I'm showing is it's just kind of in case of regular waves. So in case of regular waves, I have the same boundary conditions, but only for the pore pressure buildup. So it's 0 on the top, and then the gradient of pore pressure buildup or the accumulation of pore pressure is 0 at the bottom. And these are actually this is the another case that I validated against the experimental. I validated against the experimental, against the analytical results. And yeah, I just like wanted to show you that we also have a very good agreement with the onset of liquefaction. So here you have the pore pressure buildup against the depth of the soil, and I have it for the 4 different times. And you can see that after 2 minutes, like the pore pressure it's low, and then like after some time it really increases, and then after 15 minutes of time you can see that the top 60% of the soil is completely liquefied. So one thing to be noted is we are continuing to use the Biot equations in this setup here, but ideally actually the Biot equations are not valid after the liquefaction, because they solve only for the poroelastic solid, and then it is not a poroelastic solid anymore. And yeah, so this comes to solving a different set of equations for the I think for the pore pressure buildup. After the liquefaction, and that brings me to the. I think with respect to time, I think I have to move on with the post-liquefaction. And yeah, so this is the equations that we'll be solving in case of liquefied soil. So this is the same set of equations that I have it before, which you have the continuity equations and then the momentum balance, but like you have an additional equation for the solid fluid mixture. So for the conservation of the liquefied soil, momentum of the liquid. And yeah, so you can see here that I have an indicator function which is CL. So this you can just turn on and off whenever it is in solid, and then whenever it is in liquid. So and you can so how we go with the liquefaction after the liquefaction is we as I was telling you before, like we'll be solving for the accumulate of the pore pressure. So we'll be solving that again, and then we'll be checking for the liquefaction criteria where it is liquefied or not. And then finally there is in case of dynamic mesh, what we do is we just go through each internal phases the solid and to check whether the either side is liquefied or not. So whenever is one side is liquefied and the not other side is non-liquefied, it will just pick the phases. So whenever if it is both liquefied or not, both the sides are liquefied, or if or both the sides are non-liquefied, it will not pick up. Only if the one side is liquefied and the other side is non-liquefied, it will pick up, and then it will it does a topo changer, and what this does is it dynamically creates a boundary between the liquefied and then the non-liquefied soil, and then it modifies the mesh, and then like it comes from the next loop, and then like it will check for the accumulated pore pressure, and this loop goes on and on. So I have actually a video. I think I cannot play it from here, so I will be showing you here, and this is for the dynamic mesh. So what happens here is this is the seabed, and you can the blue part is completely the solid region, and then once red thing is the liquefied. So whenever it is liquefied, you can see that a boundary is creating between the liquefied and then the non-liquefied region. So it dynamically does it. So for the post liquefaction, I do have the same boundary conditions, but I do have a liquefaction front between the liquefied and the non-liquefied soil. So what kind of boundary condition that I use here is just a cyclic boundary condition, and that for now, like we are just satisfied with the cyclic boundary conditions, but like in the future, like we may have to change the boundary condition between the liquefied and then the non-liquefied soils. And so these are the actually I just have to add one additional parameter for this case, because like I have to have the viscosity of the soil. I think I don't have it here, but yeah, I have in the later slides, and this is the results what I have. I have this preliminary results for the post liquefaction, and this you can see that I also have a video on here, and I couldn't share it from here. Okay. Okay. Unfortunately, the video is not playing. Okay. So here you can see that this is the velocity vectors, and then you can see the seabed, there is the waves on the top, and then once it is liquefied, the pressure on the top is it's starting to increase, and then like I have a dynamically moving boundary condition here, and after some time, once it is liquefied, you can see that the behavior of the soil changes in the liquefied and then the non-liquefied regions, and this is how we would like to proceed. But right now, like we haven't done any validation cases for this post-liquefaction process, but in the future, like we will be trying to validate this model as well. And yeah, that's what like I just wanted to show you, and those of you interested can actually pick up these source code from the GitHub. And one moment, and yeah. Yeah, it is boundary is moving. Yeah, the boundary condition, the boundary is creating dynamically between the liquefied and then the non-liquefied regions, because as the time progresses, the liquefaction front progresses downwards, and then the boundary, we need to change the boundaries, because yeah, we need to separate the liquefied and then the non-liquefied regions. Yeah, okay, it's not changing the mesh entirely, but we need to create a boundary condition between that. It is maybe the number of cells, and because it's basically the number of phases changes, because sometimes you have a less number of phases when you have just a flat the whole surface, and when you have if the liquefied region is on the top, if you have some kind of a box, and then like you have a different phase, you need to have a different number of phases, so it's basically a dynamic mesh. Yeah, it is uniform, but like I haven't. No. Yeah. 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 Finally I have different, I've tried 3 different cases in which I was trying to solve the same bioequations after the liquefaction, and then like I was trying to solve 2 different viscosities, fluid with the 2 different viscosities, and for the moment we were happy that like we were able to match with the bioequations. That is because I can see in some of the analytical results that the bioequation, after the post-liquefaction, the bioequations are matching with the experimental cases. So at least for the moment, like what we have to we have is we are trying to have a we wanted to trying to compare against the same bioequations, and at least the bioequations you have the different constitutive relationships, but like this after having the Newtonian fluid, we can see that this one is like more appropriate. And so from this, like we would be trying to move ahead with validating against the post-liquefaction cases. That brings us to the summary. And yeah, so we have developed a FEM solver for using OpenFOAM, which calculates the accumulation of the pore pressure. And then the numerical model, what we have done is validated for the pore pressure, shear stress, the momentary liquefaction, and then the onset of residual liquefaction. And also after the onset of residual liquefaction, we used the dynamic mesh in order to separate the liquefied and then the non-liquefied regions. And yeah, finally, we have Navier-Stokes equations applied in case of the liquefied regions. And yeah, as I was telling you in the next steps, like we would be trying to validate this post-liquefaction model. And also the other thing what we are trying to do now is we wanted to numerically validate the plate subject to rocking motion, in which instead of waves on the top in the seabed, we would be replacing which kind of a plate, and it is vibrating such that it is behaving a kind of a wave. Okay, that's the thing that we are doing right now, and we wanted to validate that cases. So that is that we move one step ahead of analytical results, because like that cannot be done in that cannot be predicted using the analytical solutions. And then finally we would be validating this numerical model against the experimental results. And these are the references that I have used for this talk. And yeah, thank you for the attention. Do you have any other questions? I think for those of you here, I have a virtual machine for this installed. So if anyone interested can actually pick up the virtual box from me. And for also for the online participants, I guess like I would be trying to, I think we don't have right now at the cloud, but I'll be like pushing the virtual machine to the cloud in some time. Sorry? Yeah, we are doing some cases like we have we'll be doing some small scale tests in which we have waves on the seabed, and then like we already have some results, and like we are trying to validate against the experimental results for that. Sorry? Yeah. Yeah. Yeah, right now like we are done with the small scale tests, and then like no, I mean the experimental tests are done, and like we'll be validating against them, and finally we'll be moving on to the large scale in the next year. In the next year. I think I can, if there are no further questions, I can just close the session. Yeah.